Okay, so I already wrote down how you calculate my and mz. Those are the easy ones. Okay, the next section where mistakes are usually made, okay, is what do we mean by IYY and what do we mean by IZZ. Okay, most of the time, uh, yeah, we tend to make the mistake calculating what is our IYY and what is our IZZ. So I'm going to teach you a way that's easy to remember. Okay, what do we mean by IYY and IZZ? Or before I go on over there, right? Uh, one unique problem that a lot of students will have is how the moment vector works. Okay, so if we were to use right hand rule, what I tend to do is I will draw this on a piece of paper. Okay, so when you apply the moment over here, right? When you use your right hand rule, this is compression and this is tensile. And if you are not sure, what I tend to do is I will always tell students you can draw this on a piece of paper and then you start to rotate your paper. Okay, so I'm going to rotate this towards the right. Okay, so now we know that this is moment about z, and the moment about z is positive, right? And then the next one that just drawn is moment about y is also positive. Okay, then our pace again, and then our rotate right twice. Okay, so what you have over here, right? I know that the wording's gone off. This is moment about z, where the moment is negative, and then finally, I hope to be able to squeeze this one in, and I hope to rotate left. Okay. So for this case, the last case I'm showing you now, this is moment on the y-axis, and this is negative. Okay. So I usually find this really helpful. Okay. If you are having issue with right hand rule, which is gripping on the structure, I will use this technique to tell me which is tensile compression, right? So like for this case, if I move this up here, right, it's exactly the same compression on the right hand side, tensile on the left hand side, so on and so forth. So this is one technique that I will recommend you to use if you are a bit confused why when the moment is rotated or shifted, what is tensile compression. This is a good way to check. Okay, now the next thing that a lot of us make have issue is IYY and IZZ. Okay, so how to calculate IYY and IZZ? So we know that or how to calculate IZ or IYY and IZZ. Again, I will teach you a simple way to remember. So if we have our axis now, so again, this is our Y, and this is our Z, and this is rotation about X. So if this is our our structure, and for this structure, I will call this A. The dimension from here to here is A. The dimension from here to here is B. Okay, and I will copy and paste the same thing. Okay, now if we want to determine IZZ, so I'll draw down our IZZ axis first. Okay, so we want to find IZZ. So the trick is this, okay? Any geometry that's parallel to the ZZ axis will be the width. Any geometry that is perpendicular to the ZZ axis will be the depth. Okay. So IZZ is the width, depth, cube over 12. Okay. So the reference is the axis of interest. Okay. Now, if we were to draw, or if we now want to find IYY, so this is our YY axis, right? Anything that is parallel to the, I should not have drawn this, I should have drawn this as one straight line and 90 degrees. Okay, anything that's parallel to the YY axis is now known as our width, and anything that is perpendicular now, okay, so this is perpendicular, will be known as our depth. So for this case, where we want to find IYY, so the general formula is width, depth, cube divided by 12. Okay, so in summary, so I want you to be used to getting this way of finding your IYY or IZZ. Because later on, when we have compound loading, as in loading in 3D, okay, knowing which is your IYY and IZZ are critical. If you get it wrong, yeah, your stress field will have error. Okay, so in summary, the geometry parallel parallel to the axis of interest is the width, okay, and geometry perpendicular to the axis of interest is the depth. Okay, that's how I tend to remember, and that's how I will encourage you to remember. Okay, so now after talking for so long, okay, let's look at example number 1. Okay, let's look at example number 1. So example number 1, you can find the example on Avenue to Learn, I posted this image. Okay, so let's look at example number 1. So for this example, okay, you can see that the moment is has two the moment is can be broken down into two components. You can have moment about the y-axis and also the moment about the z-axis. Okay, so for this problem, we know that is classified as centric. Later on, then we do eccentric. Okay, you guys will probably remember it. Okay, so we know that the problem is centric, unsymmetrical, bending. Okay. Why is it? Because the moment has z or y and z components. Okay. And what we want to find the normal stress at point A, normal stress at point B, and normal stress at point D. Okay. And then the formula that we're going to apply will be equal to stress X is equal to my over Iyy multiplied by z minus by mz over izz multiplied by y. Okay. Now, as I said, I don't want you to focus too much whether is it plus or minus. Okay. The technique I teach you is to visualize. Okay, based on the moment vector. Okay. So what I propose now is we go for a 5 minutes break and then we come back again. So